Hi everyone, Professor Busimi here. I'd like to spend a few minutes going through the second assignment for the NLP class. First of all, you'll notice that there's a lot in common in terms of the layout here with what you saw in the first assignment. Just as before, we have a section where you can insert your name, and we also have a place where optionally you can include a homework partner's name. I just want to remind you that you're allowed to have a partner on every assignment, but I'd like it to be the case that you choose a different partner for each assignment. This is to help you meet new people in the course, get exposure to different kinds of ideas and problem-solving strategies as you work through the assignments. The goals for this particular assignment are to familiarize you with how to parse HTML data, how to perform text classification using Engram language models. We touched on Engram language models last time. We're going to talk about the classification pieces of that now. We're also going to talk about text classification using supervised machine learning algorithms. This is going to include the methods that we discussed in the lectures. And we're also going to touch on tools for sentiment analysis. Just as before, the tutorial combines active components that you are meant to do on your own, and then components that are meant to help you understand some core concepts, get familiarized with some code, and so on and so forth. And I will clearly demarcate and show you the sections that are homework related. Now, before you start this assignment, just as before, you want to pull the latest version of the course materials repository and copy homework 2 into the corresponding directory of your submission folder. You'll also want to create and attach to a virtual environment and install all the requirements I show in requirements.txt. That's this here. Lastly, when you start the notebook, just don't forget to run this initial code block here. This imports a set of tools that I've written that are going to be used later in the software. If you're interested in seeing these tools, in case you want to use them for your homework, you can access them by navigating, just as this implies, to Materials, Code, and then Utils, and you will see access to some functions that we use in the course of the assignment, including an Engram extractor function, a very simple function that counts frequency, a basic language model that's actually sort of an extension of what I asked you to do in the previous assignment, and some other components here that you're welcome to look through if you'd like. Okay, so let's get started. This week, we're going to be continuing our journey through the text of the philosophers, and more specifically, we're going to be exploring how to use natural language data for classification problems. So let's begin by returning to Project Gutenberg. That was the same text source we used in the last assignment. And notice that the website not only provides us with access to the text of Bertrand Russell's Problems of Philosophy. You can see I've got a snapshot of that here on the screen. But it also provides us with some interesting metadata in a bibliographic records section. So take a look at this down here. We have, not only is this Bertrand Russell, but we have the year. We have some information on the contents, the subject, and the language, and so on. So one interesting thing that this bibliographic record provides, of course, is the Library of Congress classification, or the LOC class, and then there's these subjects. And as we discussed in the lectures, classifications are useful because they take our messy, continuous world and they break it into these manageable groupings that we can easily act on. And thanks to Project Gutenberg classification, for example, we can see that the Problems of Philosophy is a book about, who would have guessed it, philosophy. And by knowing this classification, we may and probably will make some simplifying assumptions about the book without ever even reading a line of it. Now, it'd be useful if we could collect these bibliographic records that you see up here, in addition to the information in the raw text itself, right? We might be able to train classifiers, for instance, that predict the LOC class based on the language that's used. But in order for us to extract that information, we'll need to obtain some practice processing and extracting information from HTML-style documents. Now, I want to say here, if this is your first time ever looking at an HTML document, it might be worth you reviewing how they're formatted. To do that, there's an excellent resource here called W3 Schools. Some of you may have seen it. W3 Schools here on the left-hand side has links to not only the various components of HTML, like how are paragraphs written in HTML, they show you an example here, but it's very interactive, so you can click through and you can modify a sentence, like type some nonsense in here, click run, and it'll show you what will happen on the web page as a function of you editing the HTML document here. So if this is your first time interacting with HTML, I suggest you just poke around W3 Schools. I also received, while I'm on the note, a message from a couple of you who were asking for resources regarding Python. I wanted to note that W3 Schools also has some nice tools for teaching Python if this is your first time. So as an example, you could navigate here down to Python sets, and just as they did in the HTML case, they'll show you an example and even allow you to do some editing, right? So I can come here and put a new fruit. Let's put, well, this isn't really a fruit, but it's on my mind at this particular moment. So you can add a term to this dictionary and ask to print, and you can see it shows up here on the right-hand side. So for those of you who are new to Python, or it's your first time using it, I would take advantage of W3 Schools as well. Okay, I also want to say, before we jump into this, the reason I'm spending time in these tutorials talking about data collection is because 30% of your grade in this class comes from a project. And in that project, you're either going to take a data source that exists from somewhere, which is totally legitimate and fine, or you'll want to collect a data source potentially. And some of these components in the tutorial are to try to teach you how to collect your own data if that's the path you choose to go down. Okay, so without further ado, let's speak about collecting and processing HTML data. So before we dive into Project Gutenberg and their HTML, let's start by looking just through some simple HTML documents from a mythical social network that I personally created and stored in our code repository. I can click, for example, one of these, and you can see here that I'm actually viewing the HTML page. It's extraordinarily simple, just says a list of friends and enemies for this particular individual. I can click this and go to different pages that are available for that individual. So you'll notice that if you click through each of these, for example, here's Conroll as well, you'll notice that they each contain a list of friends and enemies with links to their friends and enemies web pages. I'm also showing you a picture of Anka.html down here. So to help us obtain some familiarity with parsing these types of documents, let's see if we can write some code to rank order these 5 mysterious figures based on the number of friends and enemies that they have mentioned in their web pages. The first step in that process is to read the HTML pages into Python. So here what I'm showing you is I've enumerated a list of the HTML documents, and for each of the files in that list, I'm opening the file, I'm reading it and storing it into the list up here, or the set, the dictionary here, and then I'm closing the file. And once I iterate through all those, I now have a dictionary with each of the file's contents within it. So I can print the contents, for example, of Anka.html using this command, and you can see that I get down here a printout of exactly what I saw in the raw file itself. Okay, well that's great. Now the trick to extracting information from HTML documents is to look for a unified structure across the documents that a parser can take advantage of. So if we inspect raw HTML of all 5 documents, you'll notice that they each contain, for example, a p class equals friend. You can see it up here, for example. And it shows up in all the other documents as well. Similarly, there's always a p class equals enemy, as you can see up here. And those sections or those paragraph tags have contained within them an A tag, right, that contains the name of the corresponding enemy or the friend. Okay, so one way we can extract this information is using what you learned last time, is with a regular expression. So I can come here and I can import the regular expression library as we did before and write a very simple function to extract the friend data. Now what this function is going to do is it's going to take one of those HTML pages and we're going to run a regular expression to find where the p tag starts, grab everything in between before the end, including where the class is equal to friend. We then want to match anything in between that paragraph tag, which is really what this first part of the block takes care of. We want to grab anything inside there before the paragraph ends. And now we have p friend. So that would hopefully is meant to grab this piece. Okay, and similarly, p enemy down here is going to grab everything where the class is enemy, the contents inside, and the end tag. So that should grab this block up here. So what I can do is for each of the pages in that HTML dictionary that we initiated together earlier, we can go about extracting the friend data and we can go ahead and store it in another dictionary that I've called data here. And so if we print that after we've run the function, you can now see that for Anka, from Anka's page, I have a list of Anka's enemies, new and Conroll, and I have, similarly for Conroll, I have a list of the enemies and the friends and so on and so forth. So using the code block above and with the regular expression knowledge that hopefully you all have some familiarity with, we were able to extract from these HTML documents some structured data that we could then use for the task that we were interested in, which, as you may recall, was rank ordering who had the most enemies and the most friends in our mythical social network. So at this point, it's very, very straightforward. We just have a simple iteration through each of the pages in the data that we created earlier. We count up the friends and the enemies, and we can now print it in a structured way to get who had the most and least in each group. So this above example was with very simple HTML data that I personally constructed just so that it takes some of the mystique and the fear out of working with HTML documents. They are a little bit intimidating if you've never worked with them because they do tend to be a mess. But again, I want to emphasize that the key is to look for structure in those documents. Okay, now you could, depending on how good you are with regular expressions, write all of your HTML parsers, and in fact, very well beyond HTML parsers with regular expressions. But if you don't want to use a regular expression, another popular tool that you could use is Python's Beautiful Soup library. Now, this tool's been around for a long time, and it's all about making your life easy when you're working with HTML style documents. And just to give you familiarity with the Beautiful Soup library, down here, let's build a tool to extract the bibliographic record information from Project Gutenberg together. Okay, so the first thing I'm going to do is I'm going to import the Beautiful Soup library. Notice that I already added it here to my requirements.txt. So assuming your virtual environment has this installed, you should get no import errors. And I'm going to import some other objects that I'm going to use for saving books later. This is JSON. This JSON library allows me to save my dictionaries to disk as JSON structures. I'm going to import a time library, which just lets me do things like pause for a certain amount of time so that we don't upset Project Gutenberg servers when we request the books very quickly. And then I'm also going to import the request library, which we used in the last assignment. Okay, so let's put together this assignment together. The first thing that we're going to want to do is get a Gutenberg book, and instead of writing out multiple code blocks for each of the books that we want to collect, I've just written a function here that takes a list of URLs, base URLs from Project Gutenberg, and we'll save the files under the save directory materials data. And once again, if you're going to be requesting data from a website, if you request it too quickly, they might think that you're attacking them. And so you oftentimes want to leave some time between the requests. So we're going to leave 2 seconds or so between each of the requests that we make. We're going to loop through each of the URLs that we pass in here. We're going to initiate a book. And what we're going to do is we're going to grab the HTML content. We're going to cast it to soup using Beautiful Soup's HTML parser right here. And then we're going to find in that soup a table with the attributes class equals files. This is where in the above table that we saw, if you could look at Project Gutenberg's page, you'll see that all the files that link to the text documents for the books are held in this files table. And similarly, when we want to get the bibliographic record information, we're going to look through the Beautiful Soup object soup, and we're going to find a table with the class attribute bibrec. Now, once we have the list of files, thanks to this class, we can navigate through there to find a href tag, which is an indication that there's a link, and ask if that href tag or the link in that table is going to a text document that's not zipped. And insofar as it is, we're going to trust that that's the text URL. And we're then going to request, using the request library, that book. And then down here, we're going to do just a little bit of housekeeping work. We're going to replace the new lines with spaces. We're going to, take care of things like replacing underscore values with blanks. This is just some housekeeping work before we finally save the JSON book to disk. Okay, so with this get Gutenberg's book function, we can come down here, and the way it gets used practically is we initiate a list of URLs that we're interested in collecting the books from. Let's take the first of these just so that it's not mysterious at all, and let's visit it. Okay, so this is Free Thought and Official Propaganda by Bertrand Russell. This is the base page. This table here, if I inspect it in my browser, you can see, if I hover over, there's the files, class, table, class equals files that I mentioned, that my soup object, I was looking for it in. And similarly down here, under the bibliographic record, there's also a table. Got to see if I can find it here. There it is. Class equals bibrec, that the object was pulling from. So basically at this level is where we're passing in the set of URLs for the books and the metadata, this bibliographic record data that we want to collect. Okay, well, if we run this tool, we're actually able to save all the books. And in case, for whatever reason, your IP address gets blocked because you are aggressively trying to collect these books, I actually included a copy of them here in data. So I have all 10 books that I used in this tutorial shipped with the repository under data. We can open up one of these. For example, let's look at Free Thought and Official Propaganda, which we were looking at on the web. And you can see here under the text section, I have a complete copy of the text that's available. If I scroll down here, you can see that all the metadata or the things in the bibliographic record are also available. I can come here and open up subject, free thought, liberalism, and propaganda show up. Or under the Library of Congress classification, there's social science and sociology. And those, in fact, exactly match what I see here on the web page. So it does seem to work. Okay, so all that function did was save the data as a JSON, and we already peeked through, but I'm showing you another example here in the code of how to open a book. For example, in this case, the future of educational institutions, and to kind of display some of the attributes of it, such as the title, the author, Library of Congress class, and so on. Okay, now let's separate the data into two corpora by author. Let's do one for Nietzsche and one for Russell. So we downloaded 5 books from each here, just like you did in the previous assignment. And we're going to perform some basic cleaning on the text to remove non-ASCII characters, convert things to lowercase, etc. while we do that. So this first section here is just importing the books. We're listing the books in the directory, we're collecting the names of the files, we're opening each, and we're appending it to a list. That's here, the data. And notice that we're only keeping the text data in this particular case. Okay, we then merge that information across the two corpora. So we initialize Nietzsche and Russell as just 2 empty strings. We cycle through the data. If the author of the data is Nietzsche, we append that data to Nietzsche, this Nietzsche string. But we sort of clean it up before we do that, because there was a little bit of garbage in those books when I was looking through them. They may not be perfectly clean, by the way, even after me doing this cleansing. And the same goes with the Russell text, right? If we see that the author is Russell, we're going to add it to this Russell string. We're going to do a little bit more pre-processing so that we only keep ASCII characters through this regular expression. Then we're going to convert all the words to lowercase as a final pre-processing step. Okay, so now at this point we have some data. We have 2 corpora, right? We have one for Nietzsche and we have one for Russell. And now that we have some text data imported and organized, we can try to build a very simple author classification model. That is, we want to build a model that can predict the author of a mysterious new sentence that we've never seen before, given some example sentences that we may have seen previously. So recall that in the last assignment, you trained 2 very simple trigram models using the works of Nietzsche and Russell. And as you saw, those language models estimate the probability of a given n-gram or sequence of n-grams according to the properties of the training data. So let's start this section of the tutorial by introducing a slightly more enhanced version of the basic language model that we covered in the last tutorial. I've written this basic language model here. This can be found over here in utils.py, right up here, in case you'd like to read through it. This basic language model, just so that we're clear on what it does, it's very similar at the core level to what we covered in the last tutorial. You notice that it has a set of given tokens, and then it has a set of next tokens, for example, out and testing. If we had this sample sentence, it notices that there's only 3 tokens. There's the token out, there's the token testing, and then there's the token this, and it's able to map out something about the next token that follows those. So for example, if we look at testing, we can see that testing is followed by this, testing is also followed by testing, and so those both show up in this key value pair here. Okay, great. But it also has a number of other features, and let's go through each of those one at a time. So the first thing that you'll notice here is that the probabilities of these 2 tokens, the next token pairs, no longer add up to 1. Well, the reason they don't add up to 1 anymore is because we applied the Laplacian smoothing assumption here. Okay, so basically I assumed that for any given token, the next token, all the other tokens in the vocabulary showed up exactly 1 time. So why is 25% missing? Well, because, out of the whole set of next tokens that occurred up here, one of those was missing. It accounted for 25% of the probability that we distributed out for the Laplacian smoothing. Okay, we also keep track of some things such as the total tokens that went into training this model. So you can come up here and count 1, 2, 3, 4, 5, 6, 7 tokens. That's the total number of tokens. We count the unique tokens, which we already mentioned are 3. There's 1, 2, 3. You can scan across the sentence and see that there are only 3. And then for each of the given n-grams, we provide a prior probability. Remember, we discussed this a little bit in the lecture. This just says, hey, if I just walk through this sentence and just count, how often does the word out show up? Not conditioned on anything, just the raw sort of incidence of this token out. And we can do the same thing for testing and get the prior and this as well. Okay, well, we also keep track of the number of blank grams. That's the number of unique tokens up here. So out of the 3 tokens that were possibilities, how many did not show up as next grams for the word out? Well, there were 3 in total. Only 1 of them showed up down here. It was testing, so that means there was 2 left. Okay, that's what that captures. And then the next one is the blank unit probabilities. That says, well, how much are each of those units? So there's 2 of them here. How much are each of those 2 worth? Well, they're each worth 0.33333. Okay, so they're each worth a third. So collectively, they're worth 2/3. And notice here, by the way, that 2/3 plus the 1/3 that comes from this sums to 1, and we get the full conditional probability from this structure. Okay, so I'm bringing this to your attention because some of you, I think, spent a little bit of time on the last assignment thinking about how to implement the Laplacian smoothing. You had a little bit of computational issues as well. And so I wanted to provide an implementation of the basic language model that was computationally efficient, that handled the Laplacian smoothing, created prior probabilities, and all sorts of other things that you might use, if not for this assignment, maybe at some point in the future for a project or something like that. Okay, so we can validate that this language model is providing sensible values by checking that the sum of the prior probabilities and the conditional probabilities equals 1. So all this code does is just says, hey, make sure that all the priors sum to 1, make sure that the conditional probabilities sum to 1, and as you can see here, in fact, they do. Okay, so one of the things we discussed in lecture 2 that we didn't get a chance to practice in the homework was this concept of backoff, right? That's the strategy of using shorter n-grams when we can't find a match for a larger n-gram. You remember the example from lecture 2. I believe it was something about an apple a day keeps the doctor away. We were looking around the neighborhood of, I think it was the word apple, and we said, hey, if we take 3 words to the right and left of that, oh, there's no matches, but if we back it out to 2 words to the right and the left of that, we can find a match, and our language model can kind of fill it in. That concept was backoff. Well, I didn't ask you to implement backoff in the homework last week, but it is actually not too difficult to implement. And instead of asking you to do it last week, I thought I would implement it myself and include it here within utils.py in a function called train backoff model. So if you come here, what you're going to see in train backoff model is that it's just very simple. We're actually just running the basic language model for a given corpora and a given gram size, n times. So we basically, if we want to have a backoff from a trigram language model, we train a trigram, we train a bigram, and we train a unigram language model so that we have all 3 of them. And if the trigram doesn't work, we can back out to the bigram. And if the bigram doesn't work, we can back out to the unigram. Okay, so we're storing this as a list of models. In the Russell case, or where we trained with Russell's data, we stored it in the Russell language model. And when we trained with the Nietzsche data, we stored it in the Nietzsche language model. Okay, great. So I can take a look, by the way, here to see that everything sort of makes sense and that there's a difference as a function of the conditional probabilities. I can come, for example, to the Russell language model and say, hey, I want to look at the unigrams, which is index 0, unigram language model, and I want to know what's the probability of doctrine given that the word was this, and I can output that probability down here. For the bigram model, I can put in 1 in this index and ask some questions about the probabilities of the next bigram given the current bigram. And similarly, I can do that for the trigram model. And we could obviously make this as big as we wanted by changing this up here. Okay, well, now that we've trained our basic language models, we can use them to assess the probabilities of new sentences being generated by the Russell and Nietzsche language models. And I wanted to show you some examples of that here. Here's some sentences. And if you know anything, by the way, about Russell and Nietzsche, you'll be familiar with some of the stylistic things in these elements that predict one of the authors versus the other. So, attain salvation through reason, attain salvation through power. I've included some blanks here as a way of testing whether my language model can kind of handle these blanks and still do a good job predicting who the author might be, even though these never show up. I mean, and the Laplacian smoothing should sort of handle that, right? So let's go ahead and predict them. Let's cycle through each of the sentences I have up here. Let's get the log probability of the sentence according to the Russell language model and the log probability of the sentence according to the Nietzsche language model. And let's just say very simply that if the probability of Russell is higher, we're going to say it's Russell. If the probability of Nietzsche is higher, we're going to say it's Nietzsche, and that's it. Well, if we come down here and we look, it actually works. I mean, I think it works pretty well, especially given that we only trained it on a few books. Attain salvation through reason. Yeah, that sounds more like Russell. Attain salvation through power. Definitely sounds like Nietzsche. Blank salvation through power. Looks like that didn't confuse it enough. It still knew that was Nietzsche. The mighty shall inherit the earth. Nietzsche. Contemplation may refine the mind is Russell, and contemplation may blank the mind. Still understood that was Russell. So this very basic language model that we have here with the backoff seems to work quite well. If, by the way, you're interested in understanding how we go about evaluating the backoff language model, once again, you can come here. This looks a lot more involved than it is when you review this code block. If you're interested in understanding how it works step by step, all you need to do is turn this flag verbose from false to true. And I've written the function so it will print to the screen step by step what it does to compute the evaluation using the language models. Okay, so let's come to learning exercise 1 now. Let me explain what you'll be doing for this first component. You're going to be taking the language model that I just showed there up above, and you're just going to be retraining it. But you're going to be retraining it using only 80% of the data. So you're going to choose 4 out of the 5 books from each of the authors. You're going to hold one of the books out. So you're going to insert the code that you use to train the models using 4 out of the 5 books in here. You're then going to test your model that you trained in part A on the 2 books that you held out. And specifically, you're going to, once you sort of tested or it created the probabilities of the sentences from those other books, the test books using the training model, you're going to do some comparisons of the probabilities of the Russell test data, for example, according to the Russell model, compared to the probabilities of the Russell test data according to the Nietzsche model, and the other way around as well. So probabilities of the Nietzsche test data according to Russell, and the probabilities of the Nietzsche test data according to Nietzsche. I'd like you to plot this in a way so that we can actually compare them. Can I see differences between, on average, how the Russell model is assigning probabilities to Russell test data versus Nietzsche test data? Do those 2 distributions of the probabilities at the sentence level look very different? They look very similar, and so on and so forth. You can insert your interpretation of the results, any interesting observations that you find or differences, insert them here. Okay, so for the second part of the tutorial, we're going to be covering better classification using Ngram language models. What do I mean by better classification? Well, in the previous section, we used two language models trained in two separate corpora to classify new sentences we had never seen before may have come from Nietzsche or Russell. Now, one deficiency of this previous approach is that our language models were trained to model the language they observed in their training data sets. They were not trained to formally discriminate between the authors of the text. We're using them that way, but that's not sort of what they were designed to do. And so for this reason, it may not be totally fair to compare the probabilities of one of the models against the other. So to illustrate this, let's train a very simple back-off language model. This is the same one we used above in the tutorial. And let's train, in fact, two of them, just like we did for Nietzsche and Russell. And just for the sake of simplicity, let's keep the n-gram size as 1. Okay, so for the first model, let's say that this is the whole universe of data. I do not care about applications A. And we train a model using that data called Model X. Okay, now similarly, we have another model that's trained with some data that's similar but a little bit different. I do not care about applications X, Y, Z. And we have a model that's trained using that data. Well, now what I can do is I can take a test sentence, like do not care, and I can evaluate, just like we did above, the probability that that test sentence came from Model X, or that that test sentence came from Model Y, right? And I can then, print those probabilities, or their log probabilities actually, for all the reasons that we've discussed in the lecture and previously. We can print those probabilities right here. Well, what do you notice here? What's really odd? Well, this trigram do not care, it only ever appears once in both texts, right? So you would intuitively think that the model should assign an equal probability to do not care in these two circumstances, but it doesn't. It says, in fact, that it's more likely that do not care came from Model X than it is that it came from Model Y. Why is that the case? What's going on here? Well, one of the ways we can investigate that is by taking a peek at the probabilities for a given unigram. So let's open up our model. So the model, it's a back-off model, so the first index is the unigram. And let's look at, for a given word do, what are the next word probabilities. And what you'll see here, if we compare Model X and Model Y down here, for Model X, the next word probability for not is different for Model X than it is for Y, even though they both only show up, that pair only shows up once here, right? In the training data for both cases. Well, why is that? That's because of the Laplacian smoothing. Look over here, we have, in this case, 6 blank grams, right? Because the total size of the vocabulary here is different, right? This guy has, I do not care about applications A. This guy has X, Y, Z. So the total size of the vocabulary on this one is 7. The total size of the vocabulary on this one is 9. And those differences in the number of unique tokens are making us kind of leak more of our probability density towards those blank tokens, so that everything can still sum up to 1 and we're not violating any rules, right? Okay, basically, because those two training data sets had a different number of grams, then consequently, there's this leakage, right? This difference in the leakage. And so that causes these two values to be different, those conditional values to be different. Now, I can go ahead and adjust for that, right? I can fix that. Well, how can I fix that? I simply can adjust by adding the missing tokens from one data set to the other, and from the other data set to the former, right? So I can sort of figure out what exists in this one, doesn't exist in this one. Okay, like for example, XYZ is here. This guy doesn't have that, so I can come and append those onto this. Similarly, A doesn't exist here. I can append that onto this, and now we're going to have the same number of unique tokens. The way I'm doing that in practice is I'm extracting the n-grams, we call it the unigrams specifically here, X and Y in this training data. And then I'm finding out what's missing from X using some set operations, what's missing from Y. And it looks like I caught, in fact, what was missing. Well, now that I've caught them, I can append them onto the AND. And I've included this kind of ridiculous token AND here just as a way of denoting that the stuff that's happening after, this point is kind of nonsense in the text, right? This isn't strictly necessary. I've just added it here as kind of a good practice. Okay, I can do this for X. I can do it for Y using the words that are missing from X and missing from Y, respectively. And I can now retrain the two models. And if I check the test sentence now, what are you going to see? Well, it looks like the total number of tokens now, or the number of blank engrams in both cases, is the same. And consequently, the conditional probability of not given do is now also the same. So that's good. We fixed that discrepancy by addressing this problem, right? Okay, but there's still another critical difference here. Notice that the prior probabilities over here are different between do for model X and do for model Y. Well, why is that the case? Well, because it depends on the total number of words that are in the training data set, right? I mean, if you want to know something about the incidence, you're going to normalize by the number of words to get these prior probabilities. So it's 7 in the case of X, and it's 11 words in the case of Y. And so as long as we're okay kind of ignoring or forgetting about this prior information, we can compare the models only according to the conditional probabilities, right? So if our goal, for example, if we think it's reasonable to throw out the prior, we can account for those differences. You can either do that by dividing the prior out, like actually dividing by whatever the value of this prior is, or to make your life simple, in my evaluate backoff model function, I've added a flag here, prior equals false, that you can just include, and the prior does not get multiplied in. And what you'll see is that if we do that and we check for those original two sentences now, we do in fact get equal probability of the trigram do not care. Okay, so in learning exercise 2, you're going to be taking some of the lessons learned from this section and kind of applying them to retrain or reperform exactly what you did in learning exercise 1. So more specifically, I want you to retrain the language models, just like you did in part 1, using 80% of the data. But I want you to augment the vocabulary of the training data to include the missing tokens, just like we did in the tutorial. We found what was missing from X, we found what was missing from Y, we augmented it, and so on. Okay, and then once again, when you're testing it, you're going to do the same thing you did in the first part. You're going to repeat the test, but I want you to do this after you've excluded the prior probabilities of the initial engram, again, as shown in this section. I then want you to compare the distributions from learning exercise 1B, so over here, to the distributions from learning exercise 2B. So you want to basically take those 4 distributions you did in 1A, take the 4 distributions you come up with here, and tell me if there's any differences between them. Comment on those differences and perform a statistical test to test if those differences are meaningful in any way. Okay, the last thing I want you to do is I want you to compare the model Perplexity. We did discuss Perplexity briefly in lecture 2. Remember, it's just a way of saying, for a given word in the language, how many other words are sort of highly likely after that word. If there's a large number of words that are highly likely for a given word, it means that the language model is highly perplex. There's not a straightforward mapping between words. If for a given word, there's only a very small number of words that follow it, the perplexity is low, and that's usually a good thing, by the way. So I want you to create a function to compute the perplexity of the basic language model. I've provided just a link here to the Wikipedia entry, which contains the equation that you can follow to compute it. It should be very straightforward for you to generate. And assess the perplexity of your language model or well, both language models and compare them here. Okay, in part 3 of this assignment, we're going to be doing classification using actual classification models. So as we saw together in the previous 2 sections, language models can be used for classification purposes by comparing the probability that a given sequence of text is generated by one author versus another. But if our objective is to classify the author of the text, then we actually don't need to spend so much time building these language models, going through all this confusing code, right? Back out and all that other stuff, right? Instead, we can just focus our attention on the classification task extremely directly, as we discussed in the lectures. So let's return to the task of sentence classification, starting with breaking our corpora into sentences. Okay, so I'm going to import NLTK. This library should be familiar to you, and what I'm going to do is I'm going to use the sentence tokenizer on the Russell and Nietzsche corpora to come up with a set of sentences for Russell and a set of sentences for Nietzsche. Okay, and I'm going to print how many sentences are in each of those. Looks like there's 12,000 in Nietzsche's books and 11,000 in the Russell books. And here's an example sentence from Russell just to make sure everything kind of looks okay. Okay, well, now what we're going to do is bag of words. We discussed this in the lecture, right? It's a very simple way of representing text documents or segments as the counts of the engrams within them. So let's come here in order to compute our bag of words representation and first extract some engrams from the sentences. Like, let's say sentence 152. We're not going to do it for all the sentences, just one of them. And then all we're going to do is count the frequency of the words in that sentence. This count frequency function is very simple. It's right here in utils up at the top. You're welcome to take a look at it. It just cycles through and counts up the number of unique entries in the list. Okay, so we can do that, and then we can print this bag of words representation. And what you see is that it's a list, or it's a dictionary that says, okay, I saw a comma show up twice in that sentence. I saw a period once. I saw and show up once, are show up once, and so on and so forth. So this is great, right? I mean, we were able to just very easily count frequency, and we have our bag of words representation. We're done. Well, we're not actually exactly done, because if you want a bag of words representation that's going to work across data sets, you have to make sure that you have that representation in the vocabulary space that spans both of those data sets. So we're not quite done here. But what's critical about this is that you can sort of see for one sentence exactly, kind of assuming this was the full vocabulary space, what it would look like. And of course, once you have it in this form, converting it to a numerical vector like this, that you can now perform statistics on or include in a machine learning model, is trivially simple. Okay, well, I already alluded to this. If you actually want to use these in reality to compare different books, you're going to need the vocabulary from all the from both sets of books. So in this case, I'm extracting unigrams from Russell, and I'm getting the set of those. I'm doing the same thing here for Nietzsche, and I'm casting that to a list. So I have the total vocabulary. I'm extracting the unigrams now from the sentence 152, the same one we showed as an example up above. And I'm just kind of appending very lazily the vocabulary words onto the unigrams so that I basically count every word exactly once. And then I'm going to, after doing the counting, I'm going to just subtract those out. So that's all this does. This was sort of my cheater's way of making sure that I account for creating a vector that has one entry for each of the unique instances in the vocabulary. It's not the most computationally efficient way, by the way. Okay, so anyway, my point here was that we can create this bag of words representation that you see here. I'm only showing the first 50 entries because obviously the vocabulary is pretty big. Okay, now fortunately, if you really want to do a bag of words representation, you don't need to do this computationally inefficient way that I showed you up here. What you can do is actually just take advantage of some pre-existing tools that compute bag of words representations for you. So In this case, we'll be using a very well-known library. In fact, I think it's well-known. If you're not familiar with it, I strongly encourage you to become familiar with it. It's a library called Sklearn. Sklearn is sort of the de facto tool for everything machine learning in the Python programming language outside of deep neural networks. Anything you're doing in machine learning other than neural nets, you'll probably be using Sklearn for it. There are a couple of rare exceptions, but I would argue that for most of the things you want to do, you can use Sklearn. It happens to have, for example, this very useful count vectorizer function that casts sentences and, in fact, entire corpora to their bag of words representation. And you can see here, for example, it turns the sentences from Russell and Nishsi into this array. It looks like a bunch of zeros, but that's because it's very sparse, and obviously it's not going to print the whole thing. But this very quickly runs and gives you a beautiful matrix that you can use then for training a classification model, for example. Okay, well, we mentioned in the lectures that if you want to train a classification model directly, you need two things, right? You need an X, which is what we generated down here, and then you need a Y, which is what is it that you want to predict. Well, let's say that we're just interested in predicting who the author of a text is, like we were doing in the previous parts of the assignment. We can just append a set of ones and zeros together that are equal to the length of the number of sentences, and we now have our Y vector that we're going to use for classification tasks. So where you come in all this, in learning exercise 3, is running some of those classifiers. Now, what I'm going to ask you to do in this learning exercise is not build the classifiers from scratch. I thought about having you do that, but I think if you get used to how the classifiers work by using them first a little bit, if you haven't already in some other context, going in and taking a look at the source code or an implementation will be significantly easier. So what I'd like you to do in this assignment is play around with naive Bayes, logistic regression, and a penalized logistic regression to predict the author of a text given the bag of words representation that we just came up with. Okay, so in part A, you're going to train and assess the naive Bayes model. You should be familiar with this and how it works from the lecture already. What I've done is I've included below a code block that shows you how to import the right packages from Sklearn, how to split the training data into an 80%, 20% kind of set for training your model and testing it, how to initialize a naive Bayes model, fit the classifier, predict the outcomes, and generate a confusion matrix. Again, this should be all familiar to you from the lecture, sort of what's going on in the guts of each of these. Okay, well, in this first part, you're going to take this code block and you're going to use, instead of unigrams like I did here, you're going to use bigrams instead as the quote-unquote words in the bag of words model. And instead of doing an 80-20 split here, you're going to do tenfold cross-validation. And you're also going to report the mean and the standard deviation of the following performance metrics across the tenfolds. You're going to report the accuracy, so mean and standard deviation of that, of the precision, the recall, and the area under the receiver operator curve. Notice that these 4 performance metrics, I have not included them down here. You will need to implement those, and because I believe that understanding the performance metrics is absolutely critical to the use of these classification models, I would like you to write those functions on your own. I don't want you to use the ones in Sklearn. I want you to write the functions to compute accuracy, precision, recall, and area under the receiver operating curve on your own when you're using them down here. And of course, comment on your results as you see fit. Okay, the next thing you're going to do is you're going to construct a data set that highlights the limitations of naive Bayes. If you watched the lecture and you understood the example, I think this should be hopefully pretty easy to do. I just want you to construct an example data set of 10 to 20 sentences that highlights how the feature independence assumptions of naive Bayes can lead to poor performance. Then you train a naive Bayes classifier using the data set and kind of demonstrate to me the corner cases where naive Bayes fails. Okay, then I want you to train finally in this last part, well, it's not quite the last part, other models and compare their performance against naive Bayes. So specifically, I want you to plot a receiver operator curve and a calibration plot for each of the models listed below on a given 80-20 split of your data. So you don't need to do tenfold cross-validation here, just an 80-20 split. I want you to train a naive Bayes classification model. I want you to compare that against the Sklearn logistic regression model. And I want you to compare that against the Sklearn elastic net. Elastic net, by the way, is the regularized version of logistic regression that contains both an L1 and an L2 penalty, just like we discussed in the lectures. So that's the difference between these two models here. Where I'm going to rely on you to be creative is to plot the results in a way that it makes it easy for me to compare them across the 4 models. If one of your models fails to converge, for example, due to collinearities, don't worry, just report that in your results. Okay, so in this part, this last section of learning exercise 3, I want you to explore the impact of vocabulary on the model performance. So I want you to repeat the procedure in part C, that's the one up here, after reducing the number of features in your bag of words representation. More specifically, I want you to regenerate the plots after removing the bottom 1% of n-grams by rank, the bottom 10% of n-grams by rank, the bottom 25%, the top 1%, the top 10%, and the top 25%. And then I want you to comment on any differences you see and speculate on why those differences exist. You can insert your code and a discussion of what you observe here. Okay, finally now we're in the last part of the tutorial. And this one should be, I dare say, easy and fun. Has to do with sentiment classification. So everything we've done up till now in the previous sections of the assignment, we had demonstrated how to train a model that classifies an author using bag of words or using a language model. And we were able to accomplish, at least in the case of the supervised models, we saw that creating the training data and training the models is actually very, very simple. It's super fast. Well, these sentence author classification problems are kind of convenient, right? Because we can generate a ton of supervised training data because I go to each book has tons of sentences, and so I can just assign the author of that book to each of the sentences and generate lots and lots and lots of training data to use. But of course, not all classification problems in NLP are this straightforward. For example, let's say that you wanted to classify the sentiment of the sentences in Russell and Nietzsche. How would you go about collecting a training data set for that? Would you have someone painstakingly sit through and label each of the sentences? And there's also a further question, which we alluded to in lectures about, should sentiment even be cast as a binary classification problem? It exists on a spectrum after all. So one of the solutions to this problem for this stage that we're in the semester, we're going to talk more about sentiment analysis and classification, to all those sorts of techniques later as well. But for this stage in the semester, there's a simple way that we can handle sentiment problem, which is to simply compute the sentiment of the text based on the properties of the sentiment of the words that make up the sentence, right? So if a sentence has 3 words, I can just naively say, I'm going to look at those 3 words, I'm going to find out something about the sentiment of those, and then I'm going to sum it, take the average or some other thing to get the sentiment of the sentence. Now, fortunately for us, or for you rather, there are resources that help with providing those estimates of the word sentiment. One of those resources is SentiWordNet here. I've provided a link to it. And this is a publicly available resource for opinion mining, they call it. It basically says, for all the various words in the English language, in all their various contexts, tell me what the sentiment is on a normalized scale. And that's what SentiWordNet provides. Specifically, it's providing the sentiment as positive, negative, and objective. Okay, and they always range between 0 and 1. You can download it from this address here, but I've also included a copy of it within our repo, so when you've pulled this, you'll have a copy of it in case you can't get it from the web. Okay, so let's start by initializing a dictionary to store sentiment of each of the words in. Let's open up the source of the data that I stored locally within our repo at materials sentiwordnet.txt. Let's read the CSV, which happens to be tab delimited, and let's loop through each line of the CSV, get the headers. If it's not a header, let's store the value of the word and its sentiment in the dictionary. Specifically, we're going to take the positive score and the negative score that's reported. And with it imported, it's very easy to check what the sentiment of a word is. Right? With this, we can just come here and say, tell me the sentiment of the word happy. The number 1 here, by the way, is because SentiWordNet is trying to find multiple instances of the use of the word happy. So if you want just the most common instance, you always tag the number 1 after the keyword you're interested in. So this means the most common use of the word happy that they studied had this kind of a sentiment. It was 85.7 or 87.5 positive score, 0 negative score. Okay, well, how about sad? The word sad in its first most common use was 0.125 positive score and 0.75 negative score. Now, this can be a little bit confusing, right? Because we think of positive and negative as adversarial. They're at odds with each other. You can't have both. But SentiWordNet reports both of these values together. And they're not always opposites of one another, so to speak. So because of that, you can simplify it down by simply taking the difference between two scores here. And you can get a single floating point value that represents, for example, in the case of sad, a negative if they're more sad than they were happy, or more negative than they were positive, and a positive number if they were more positive than they were negative. Now, in this last learning exercise, I'm going to ask you to extract the word level sentiment provided by SentiWordNet to score all the words in the Russell and Richey texts. And specifically, I want you to sum the sentiment of all words in each of the sentences divided by the total number of words so that you get basically the average sentiment per sentence according to sentiword.net. And then I want you to generate 2 histograms that compare the empirical distributions of the sentence sentiments for the 2 authors, and compare any differences between the distributions, comment on if they're statistically significant or not. And just as I did above, by the way, please assume that just the first sense of the word in sentiword.net is what you should use. So this number 1 here, make sure you append it to the end to get the sense. There's probably going to be some cases where the words don't show up. If they don't show up, you can just neglect them. Insert your code and, of course, your interpretation of results here, and you're done with that part. Now, the last thing in the learning exercise is the use of sentiment as a feature. So what I want you to do is train a logistic regression model, which takes as an input a bag of words representation of the sentences. You can do unigrams, and I want you to take the sentence sentiment that you just computed above, right? So you should have a bag of words representation. That's a matrix. You add an additional column to that matrix, which is the sentence sentiment. And I want you to see if you can try to predict the identity of the author, just like we did in learning exercise 3, using this new model. But in this case, I want you to actually take the odds ratio of the coefficient that describes the importance of the sentiment feature and interpret what that odds ratio means. If your model does not converge, it's possible, if not likely, that this will occur. I'd like you to propose a coherent strategy to remove bag of words based features until it does. Okay, and that's it. The last thing that you will have to do is your self-assessment, where once again, you're going to provide an assessment of how successfully you accomplished the learning exercise in the assignment according to the instructions provided. You will not provide or assign yourself points for effort, just for what you accomplished according to the instructions. And I'm going to use this as a starting point when I grade you, just like I did last time. Once again, as a reminder, if you underestimate this grade, you won't get a penalty. If you overestimate this grade, you will. So err on the side of caution, be as honest as possible. It'll save us a lot of drama in the future.